Hi everyone. So Barcelona-Computing. So in the last years, we've seen a lot of research trying to run what's basically massively parallel processing applications using function as a service. So we have both data and compute-intensive applications. That's analytics, machine learning, a bunch of examples here, and there has been a lot of papers doing that from 2017 until now, basically. So why is that? But in some, we think it's because of the burstability of the function as a service paradigm. And this table, I think it shows it clearly. If we want to use traditional engines in a more ephemeral way, these engines take quite a bit of seconds to start up and be ready to start processing. And instead, with FaaS, and we see them in the lower part of the table, with either Knative or OpenWhisk, we are already in 2-digit seconds, and with AWS Lambda, we are already having pools of thousands of CPUs in just seconds. So these resources are given to you on demand, fine-grained, very scalable. You don't pay for idle, and you basically don't have to do any resource configurations. So they are ideal for what we call bursts, which are short, sudden, and massively parallel tasks. And it introduces this idea of changing the mindset from a cluster-centric, or managing a cluster, into the job-centric kind of way to use the resources. So you ask resources for a single job. The problem of this is that FaaS was not designed for this kind of data processing applications. It's designed for event-based applications, so the workers, the functions are ephemeral, they are isolated individually, they are stateless, so we don't have parallelism between workers or functions that is guaranteed. We don't have communication between these workers. So instead, these applications that are massively parallel processing are mostly stateful. So we need these workers to collaborate, and this is a problem. And these applications could be sorting, could be joins, table joins, order aggregations, and many more. So basically, the conclusion is that FaaS is not enough. We need something else. In the literature, because we have a lot of literature on doing these stateful things on function as a service, we've seen a lot of solutions that basically sidestep the limitations of FaaS. And what they do is like allowing communication using indirect communication with remote storage, also not traversal, for instance. We have also seen some works doing some opportunistic placement of if you invoke the same function twice, maybe it reuses the container or runs on the same container, for instance, and other things. So this brings us to our prime research question, which is, for this kind of programs, do we need this isolation on a per worker basis, or should we do something else? So why are we sticking with FaaS, and why don't we try to basically evolve FaaS to support this kind of applications instead? So with that in mind, we basically identified what's the problem in FaaS for this kind of applications, and found or defined 3 friction points. The first one is, of course, that workers are isolated one by one. So this means that we need to invoke them one by one. And this creates skewed startup times, and also redundant setup, like code duplication. You need to load everything for each individual worker. This in time provokes that when you need to orchestrate all these workers, it's very complex. It's a complex orchestration. You need to fragment the job into multiple workers that are invoked independently, so it may be a problem. And because these workers are difficult to coordinate and isolated, we end up with a lot of huge data movement between the workers to just coordinate them or progress in work. So yes, this is a bit of the problem we are dealing here. So we presented Bar's computing, which is a new paradigm for running these massively parallel processing jobs. And it's evolving fast and introduces three concepts, which are group awareness, packing, and locality exploitation. So the first one is we raise this level of isolation from one worker to the whole job. So the platform now knows that we want to run a full job, so it's a group, and you can manage the resources with that in mind. So this is implemented with a Flare primitive, which is basically a group invocation that guarantees parallelism for all workers. And because parallelism is guaranteed, we can do synchronous execution between all these workers. Then, because the platform knows that all workers are running at the same time, we can do optimizations, like packing workers in fewer containers so that it's faster to start the execution and optimize the execution. And finally, because we are packing workers together, these workers have locality that we can exploit for communication in memory in the same memory, zero copy communication. So how this works in the architecture is basically how this solves all the frictions that I said before. The first one of worker isolation is pretty clear. Before we had to run a lot of invocations. Now we only have one invocation, and the platform already can manage everything as a single job. The job fragmentation is completely changed because now that the platform knows that it's a job, we don't need to have this external orchestrator that manages all the functions and tells when to execute each of these ones, but it's the whole job that can coordinate the execution by itself. So we basically remove the orchestration from externally. And third, before all communication between each individual worker had to pass through an external communication service, and now this communication is greatly reduced because we have packs where the execution, the communication is done locally. So how this worker packing works, basically we've defined the granularity, which is the number of workers that fit into a pack. And the key question here is what's the correct granularity, how much do we want to pack the workers? And this is basically a trade-off between the amount of locality that we will get from the scheduling, but also in the other side, the complexity of finding these resources correctly within the resource space of the platform. So basically, we see three possible strategies here. The first one would be, okay, we want the maximum locality. Let's make the containers the biggest possible, the packs the biggest as possible, but this creates resource fragmentation, like single CPUs that may be left out and never be used because it's impossible to find a good placement there. The other possibility is to do all the packs of the same size. So it's easier. And the one that combines, and the one that we use is the mixed one, that it's basically, okay, we find the packs in a fixed size, but if more than one of these packs end up on the same machine, we can group them together to maximize locality. Okay, so basically this is the structure. It's very similar to a FaaS platform. You would deploy a a function like this one here, and basically you will trigger a job that runs this function. The difference is that, of course, the invoker machines will create this pack and provide the BCM, the burst communication middleware, to abstract the communication between the workers and provide what is basically done here. And you will see in the burst context that allows workers to perform collectives like broadcasts or reduce or all-to-all, and other things like that may be needed to perform work in this model. So very fast over the evaluation. You can check the full details on the paper. Basically, the first result would be in worker parallelism. With burst computing, we improve a lot worker simultaneity. We are able to guarantee parallelism of the execution, and this also helps reducing the startup time of all the execution of all the workers. So if we had with OpenWhisk, we had like 20 seconds to have these 960 workers. Now we are able to have all these 960 workers completely parallel in just 1.7 seconds, which is 40 times faster. Next, we have also a lot of reduction in the data movement that's remote between the workers. And we show this with two collectives, broadcast and all-to-all. And the reduction obviously depends on the granularity. As higher is the granularity, we will have more communication that is local. So the less communication will happen remotely. And this affects both the amount of data that we transfer and obviously the speed of the collective that we perform. So more generally, we tested the burst computing with a terasort. And this is interesting because it's a stateful problem that requires, in function as a service, requires two stages to perform the shuffle in between. So it's a bit complex and requires these two stages that generate this gap in the middle where no functions are running. In fact, the second stage is waiting for one of the outliers. You may see that, and it basically slows the whole process. Instead, with bursts, we only have a single stage that is able to communicate, and thanks to locality, we speed up a lot the communication and achieve in global a 2 times speed up in this case. Next, another interesting application is PageRun. This is interesting because it's very hard to do with vanilla FaaS because it's an iterative application that needs to coordinate all workers several times over time. So this is very intensive in communication, and you will see in the plot that this is actually what happens. With workers that are isolated, we have a lot of overhead of the communication because it's constantly doing the sharing of the common vector that needs to be replicated to all workers. And as we increase the granularity, the time of communication quickly decreases. So basically, we remove about 98% of the amount of data that we transfer and improve execution time by 13 times. So to conclude, basically FaaS, we've seen that is not enough. We've seen that it's used for postability, which is correct and it's good, but bursts or massively parallel processes are usually stateful, or there are a lot of stateful applications, so we identified these 3 frictions. And we presented burst computing, which introduces group awareness to the platform so that we can have worker packing to optimize the scheduling of resources and provide locality, and solve these frictions with the Flare primitive, which is a group invocation, guaranteed parallelism to allow worker collaboration effectively, and Locality to minimize the communication that is remote in this platform. So thank you for your attention. You can contact me by email, and all the code of Bar's computing is available online on GitHub.